Welcome back. I'm Muggsy, and today I'm going to explain ionic bonding. Now, if you don't already know about ions, you should check out my video on that. But assuming you do, let's just start talking about how ions come together to form ionic compounds. Sodium, as I said earlier, is an incredibly reactive metal. It explodes when you put it in water, and so almost none of the sodium we find in the world exists in that pure elemental state. Chlorine is an incredibly corrosive and toxic gas that also is highly reactive with anything it encounters. And so almost none of the chlorine out there in the world exists as chlorine gas. But when they come together, they form sodium chloride. Table salt, an incredibly common substance, an ionic compound, and our oceans are just full of this stuff. And so when elements become ions to become stable, they bond together to form ionic compounds, which are all over the world, all around us. Let's look at how they do this. So with the example of sodium, you can see that it's in column 1A of the periodic table. It's an alkali metal, and so it has one valence electron. When it loses that one valence electron, it's going to gain a positive charge, but let's just leave that valence electron on it for now. Chlorine is all the way on column 17 of the periodic table, or 7A, and it's what's known as a halogen. It has 7 valence electrons. Again, if you don't know how to calculate these valence electrons, you should go ahead and check out my earlier video on them. Okay, now we said it's easier for sodium to lose one valence electron to become stable than gain 7. Because remember, elements want to have a stable outer level of electrons, or octet, which typically is 8 electrons. Chlorine has 7 out of 8, so it just needs to gain 1 electron. So the way we did it earlier is sodium just kind of sends this electron out into space, and chlorine just gains an electron from space. But obviously, because of the first law of thermodynamics, you can't just get something from nothing. Everything has to go somewhere, and everything has to come from somewhere. And so what actually happens is when chlorine gains that electron, it's gaining it from an element like sodium. So sodium gives up its 1 electron and it goes to chlorine. Now sodium has lost an electron. So sodium has a charge of +1, which we just draw as a plus sign in the upper right-hand corner of the atomic symbol. And chlorine now has gained an electron, so it has a charge of -1, which we draw as just a negative sign in the upper right-hand corner as well. Now, what do positive and negatively charged things do? They attract each other. So now these two are going to be attached close to each other. And so we have sodium chloride, the chemical compound that's made from sodium and chlorine bonding together. We call this process of some elements giving up electrons to other elements which accept those electrons, we call that ionic bonding, because they form ions and in the process they bond with each other, and they're no longer pure elements, they're now an ionic chemical compound. As you might recall from an earlier video, the NaCl is just a chemical formula, and that's telling us that this is an ionic compound made of 1 sodium and 1 chlorine stuck together. When it's all together as a compound, you actually don't need to write the charges out anymore. You can just write NaCl, and the charges are implied because at this point you'll kind of understand that the sodium is going to have a positive charge and the chlorine is going to have a minus charge. Okay, that was just one example. I'll give you lots more so we can really understand this concept of how elements give up and take electrons from other elements to form ionic compounds. Let's look at the example of lithium and nitrogen. Okay, if we were to draw the Lewis structures of lithium and nitrogen, we'd see that lithium has 1 valence electron and nitrogen has 5. So if these two were forming an ionic bond together, we would know that lithium's the one that needs to give up electrons, and nitrogen is the one that needs to receive those electrons. Because nitrogen needs to receive 3 to become stable, because 5 plus 3 is 8. And lithium needs to give up 1 to become stable, because 1 minus 1 is 0, which will take us back to the previous energy level, which will be full. Okay, so lithium's going to give up its 1 electron here to nitrogen. Now lithium is totally stable and happy. It has a charge of +1. Nitrogen has a charge of -1. But we're not done. That nitrogen isn't stable. It now has 1, 2, 3, 4, 5, 6 valence electrons. And it wants to have 8, so it still needs to gain 2 more. But it can't get any more from this lithium atom because it's now become a lithium ion and it's totally stable. It doesn't want to give up any more electrons because if it does, that will make it unstable, which defeats the whole purpose. But fortunately, when you're having chemical reactions, there isn't just one lithium atom and one nitrogen atom. You know, atoms are so incredibly small that even if you had a drop of one liquid and a drop of another liquid, they would be full of billions and billions and probably more than that atoms. There's massive numbers of atoms. So we're assuming this reaction is taking place and there are lots of other lithiums and nitrogens around. So that means this nitrogen needs to keep gaining electrons. There are other lithiums around to give them up. So the way I do this is I just draw lithium over here now. I put its valence electron facing the nitrogen, although you don't really need to, I just do that for me. And it's going to give up that electron to the nitrogen. It's going to lose it, and in doing so, this lithium is going to gain a charge of +1. The nitrogen has now picked up 2 electrons, so it has a charge of 2-. But again, it's still not happy. It has 7 out of 8 electrons. So it's going to need to gain 1 more, so we're going to need another lithium. So I'll put a lithium down here. It's got 1 valence electron. It's going to give that up to nitrogen, so that's going to go up here. This lithium's now happy. It's given up its 1 valence electron. The nitrogen has now gained 3 valence electrons. And the nitrogen is finally stable. It has 8 out of 8, a full octet. So in this instance, it's taken 3 lithiums to make the ionic compound with nitrogen where everyone is stable. Now, if I were to write out the chemical formula for this compound that we just formed, there's a convention, and that is the positively charged thing goes first, typically the metal, which is this lithium here, and then the negatively charged thing goes second. So we would put lithium first, then we would put nitrogen, and then we would have to account for how many atoms there are. Just like we do with any chemical formula, there's 3 lithiums, so we put a little 3 there. And there's 1 nitrogen, so I think I might make a mistake, but I'm going to put a little 1 here. And oops, it seems like I made a mistake. Remember, just like x in algebra, you don't need to say 1x, you just say x. And just like with +1, we don't write +1, we just write plus. If there's 1 of an element in the chemical formula, you don't need a subscript after it, you just leave it as the atomic symbol. So Li3N is what we've just made when we chemically bond lithium and nitrogen together. We call this lithium nitride, but I'll have a later video explaining how to name ionic compounds. Let's look at another example. Okay, let's look at an example of calcium bonding with oxygen. Calcium is in column 2 of the periodic table. It's an alkaline earth metal, so that means it has 2 valence electrons. And because I assume those are going to interact with the oxygen, I kind of like to draw them on the sides that are easier to interact with oxygen, so I probably wouldn't draw them over here, but that doesn't matter. You could do that if you want. This is just easier for me. Oxygen's in column 6A of the periodic table, so therefore it's got 6 valence electrons. And so I'm going to have my 2 open sides be kind of where they can interact with that calcium. Again, you don't need to do that. That's just easier for me. Remember, you put 1 electron on each side before you double them up. That's just basic Lewis structures. And then let's talk about what's easiest here. Calcium has 2, so it's going to be easy for it to lose those 2 valence electrons, so it's going to want to send them somewhere. Oxygen has 6, so it's going to want to gain 2 to get 8. Well, it just so happens we have 2 right here, so this one's going to go there. This one's going to go there. In the process, calcium just gave up 2 electrons, so it gets a charge of 2 plus. And oxygen has just gained 2 electrons, so it has a charge of 2 minus, and they're both stable. So this was a really easy problem. The chemical formula of this guy is just, we put the positively charged thing first, that's the calcium, typically the metal, and then the negatively charged thing second. Call this calcium oxide. That was a really easy example. You just need 1 calcium and 1 oxygen. What if we had a more complicated example, such as aluminum and oxygen? Now, this time it's a little bit trickier because aluminum is in column 3A of the periodic table, so it has 3 valence electrons. Oxygen is in column 6A, so it has 6 valence electrons. Aluminum needs to lose 3, and oxygen needs to gain 2. So let's have aluminum give one of its electrons to oxygen here, and the other one to oxygen here. And now that oxygen is fully stable. It has a charge of 2 minus, and the aluminum has a charge of 2 plus. And the oxygen is great. It now has 8 valence electrons, but the aluminum isn't. It still has 1 valence electron that it needs to get rid of. So let's add something that can take that valence electron from the aluminum, and assuming the only thing in our beaker is aluminum and oxygen, we're going to need to add another oxygen atom. So I'm going to put it down below the aluminum here. Oops, I guess I was doing those in yellow, wasn't I? Let's put an oxygen down here, and let's give it 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay, and it can take this valence electron from aluminum, which now has a charge of 3 plus, and now has no valence electrons remaining, so it's totally stable. This oxygen now has a charge of -1, but it's not stable because it now has 1, 2, 3, 4, 5, 6, 7 out of 8 electrons. So it still needs to receive 1 more electron to become stable. So let's add another aluminum, which, as you know by now, has 3 valence electrons. And it's going to give, let's say, 1 of those to oxygen. Now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. It's totally happy, but it's received 2 to do that. So it now has a charge of 2 minus. This aluminum now has a charge of +1. And both oxygens are stable. This aluminum is stable, but this new aluminum is now unstable. Okay, let's keep going. Let's add 1 more oxygen. Again, this has 6 valence electrons, 1, 2, 3, 4, 5, 6. I'm going to leave my open ones on this side because I assume they're going to interact with this aluminum here, hint, hint. This aluminum is going to give up both of its remaining electrons to this oxygen, and in the process, it'll become totally stable and gain a +3 charge, or 3 plus. The oxygen now has gained 2 electrons, which gives it a 2 minus charge. And in doing so, has become stable. It now has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, 8 out of 8. So it's perfectly stable. So if we were to write the chemical formula of this whole big thing, we would put which element first? If you said aluminum, you're correct because it is the positively charged thing. And how many aluminums do we have? 1, 2. So let's put a little 2 subscript. Then we put the oxygen because it's the negatively charged ion. We have 3 oxygens, so we put a little 3 after it. And this is the chemical formula of the ionic compound we just created, aluminum oxide. A little bit of terminology real quick. The positively charged ions we call cations. And the way I think of it is in the word cat, there's this plus sign right here. So that'll help you kind of remember that's called a cation. And then our negatively charged ions, like this oxygen, we call anions. And the way I remember this is that "an" in front of a word usually means negative. What's a good example of this? Okay, I can't think of one off the top of my head. Okay, as you can see, this was kind of a much more complicated example, but really all you need to do is keep adding either cations or anions until the whole thing is stable. There's kind of a shortcut you can do, and that is aluminum has 3 valence electrons, so its ion has a charge of 3+. And oxygen has a charge of 2- when it forms an ion. So if you just balance these charges, that is, you find coefficients that will make them equal 0, you could just do it that way and you wouldn't need to keep drawing them out like I did here. So for instance, the lowest common factor of 3 and 2 is 6. And in order to get 6, I'm going to need 2 aluminums, 2 times 3 is 6, and I'm going to need 3 oxygens, 3 times 2 is 6. And so now I'm going to have a total positive charge of +6 over here. I'm going to have a total negative charge of -6, and they're going to equal out. And that's an important thing to remember about ionic compounds, that even though ions have positive and negative charges, this aluminum has a charge of +3, oxygen has a charge of -2, the ionic compound itself, when they come together, is neutral. The charges equal 0, right? Because all those positives are attracting an equal number of negatives. So this shortcut method is just create the charge, find the lowest common factor, and then do it that way. I'll show you another example real quick. If I gave you the example, for example, of magnesium fluoride, you could just do it this way. Magnesium has 2 valence electrons, so it's going to lose those 2 to become stable, giving it a charge of +2. Fluorine has 7 valence electrons. It's going to gain 1 to become stable, giving it a charge of -1. If we want to make these 2 charges equal, we're just going to need 2 fluorines to every 1 magnesium, or you could say it this way: the lowest common factor of 2 and 1 is 2. So we're just going to need 1 of these and 2 of these. So if we just put a little 2 after the F, we now have the stable ionic compound magnesium fluoride. And again, we're not drawing out all the Lewis structures these time, because all we're trying to do is just make the charges equal. If this is +2 and this is -1, we're going to need 2 -1s to equal that 1 + 2. So we just put a little 2 after the F. Let's do another example real quick, and then I think we'll be done with ionic compounds. Let's say we have phosphorus, and let's say we have calcium. Phosphorus has 5 valence electrons, so it's going to gain 3 to become stable, giving it a charge of 3-. Calcium has 2 valence electrons. It's in column 2A, so it's going to lose 2 to become stable, giving it a charge of 2+. The smallest common factor of 3 and 2 is 6, so we're going to need 2 -3s to get -6, and 3 + 2s to get +6. And so we end up with 2 phosphoruses and 3 calciums. Now, remember, the positively charged thing, the calcium, the cation, always goes first in the chemical formula. So it's not going to be P2Ca3, it's going to be Ca3P2. Cation first and then the anion to make calcium phosphide. Okay, making ionic compounds is a lot of fun. I think it's pretty easy, especially once you get the hang of it. Have fun with it, and I'll see you next time.